The James Webb Space Telescope was hit by a micrometeoroid which damaged one of its mirrors. The impact occurred sometime between May 22nd and 25th. Now, if we didn't know any better, that would sound pretty bad. And the truth is that it's not great news, but it's also the truth that Webb is really doing just fine. In fact, in a blog post explaining the overall situation, NASA announced that Webb is still performing better than it needs to for science. The impact occurred during instrument commissioning in late May when the mission team started to notice a slight degradation in the image quality coming down from the telescope. Now, NASA hasn't released any images that demonstrate this, so I don't know if this was a tiny blur or some scattered light or something else entirely. But however the distortion manifested itself in the data, the team were able to work backwards to conclude that it was a micrometeoroid impact on the C3 mirror segment. Now, micrometeoroids are tiny particles that are typically about the size of a grain of sand. However, those cosmic sand grains are moving at tens of kilometers per second. So even though the sand grains are very tiny, they're still packing a lot of kinetic energy. So that means impacts like these are inevitable. Spacecraft get hit like this all the time. In fact, how much they get hit depends a great deal on their location. A low Earth orbit is particularly bad because there's a lot of debris trapped there. The Hubble Space Telescope has been pelted by micrometeoroids pretty much non-stop since it was launched in 1990. The Sun-Earth L2 environment is considered to be safer overall because it is gravitationally metastable. And that means particles easily drift in and out of this region rather than linger around and build up over time. So while the chances of an individual impact are expected to be a little bit lower at L2, that doesn't mean that impacts are never going to happen. ESA's Gaia satellite is still out there, getting pelted every now and again since 2013. So the fact that Webb was hit at least 5 times since it launched is really not surprising. In fact, it's pretty much in line with the predicted frequency of impacts. But this particular May impact has gotten quite a bit of extra attention because not only did it strike one of the mirror segments, but it was also larger than anticipated. And to make matters more interesting, the impact was beyond what engineers could have tested on the ground before launch. Now, to be clear, it's not that larger impacts were not expected to happen, but rather they were just expected to occur much less often than normal impacts. But the fact that Webb suffered such a relatively large impact so early on in its mission raises the question of whether Webb was just really unlucky this time, or if there is some misunderstanding of the dust environment at L2. But either way, Webb is going to be more sensitive to impacts like these because it has the largest mirror ever flown, and that mirror is exposed to open space. More on that in a moment. But for now, the first order of business was to correct for the distortions to the image. To that end, a team of optical engineers got together to analyze the effects of the impact and work backward to determine the exact adjustments that would be necessary. Now, the blog post doesn't say exactly how they went about doing this, but I suspect they may have used the same phase retrieval algorithm to determine just how far out of alignment or how far out of phase the C3 mirror was relative to the other segments. Now, I talked about how the phasing process works in a previous video, so feel free to check that out if you want to get caught up on all those details. But the short version is that each mirror segment is backed by a hexapod of 6 actuators. Together, they can adjust the segment's yaw, pitch, roll, and its position relative to the other mirrors. A 7th central actuator can even adjust the shape of the segment by increasing or decreasing its radius of curvature. So far, the team have already made at least one set of adjustments to the C3 segment, and they've managed to cancel out some of the degradation this way. Now, the blog post indicates that the team were still analyzing the effects of these adjustments, and they'll probably go back and make some additional corrections until everything is as close to just exactly perfect as they can get it. Now, by the way, I know it would have been really nice to have a camera on board Webb to image the mirror segments and evaluate the damage. But mounting a camera that could operate at cryogenic temperatures and zoom in to inspect the mirrors at that level of detail turned out to be far more complex and added too much risk to the mission. Still, Webb's NIRCam instrument does have the ability to image the mirrors with its pupil imaging lens. And we saw this in a selfie image that was released during phasing. Now, I don't know if they attempted to image the mirrors this way, but I would be surprised if a selfie would have revealed anything. And that's because micrometeoroid impacts are on the order of just a millimeter or so in size. A ding that small would probably not even show up in any selfie image. Still, a tiny ding like that would produce a small but measurable degradation in the overall image quality. Now, to be clear, this micrometeoroid impact doesn't really pose any impact to science. But how is that even possible? And isn't Webb's mission going to have to last longer than 20 years? How is it going to continue to do that without just getting pummeled to death? Well, the answer is, yeah, it actually will eventually get pummeled to death, but that would be long after its mission ended. And even during its mission, micrometeoroids are not the only threat to the Webb telescope. It'll continue to get hammered by ultraviolet sunlight and solar wind particles trying to break down Webb's sunshield. And cosmic rays that were accelerated in gamma ray bursts and in supernovae will relentlessly smash through Webb at a huge fraction of the speed of light. And that's why Webb was over-engineered from the outset to perform way above the levels needed for science. In other words, it was built with plenty of performance margin in its optical, thermal, mechanical, and electrical systems. For example, its thermal shield layers include ripstops that prevent a single puncture from rendering the entire layer useless. And it incorporates more shield layers than are strictly necessary to keep Webb cooled to the required temperatures. Likewise, the mirror's image quality is much higher than is needed for science. In a worst-case scenario, if a mirror segment gets totally smashed to the point where it can no longer contribute to the science, engineers can even pivot that mirror segment out of the line of sight and essentially take away its contribution to the science instruments. And the instruments, by the way, are also the most sensitive and delicate components on board Webb. And that's why they're physically shielded by the surrounding science instrument module. Now, as Webb orbits the Sun, it will occasionally pass through the tails of long extinct comets. We see their effects all the time here on Earth in the form of meteor showers. When those events occur, Webb will be turned such that its backside is facing into the oncoming debris. And by the way, this is part of the reason why everything was kept to such insanely high cleanliness standards while Webb was still on the ground. Engineers knew that Webb would accumulate space dust during those meteor showers, so starting out as clean as possible helps to maximize its performance over its mission. Still, the impacts that Webb has endured thus far weren't part of any meteor showers. They were just random grains of dust flying around out there. So that raises the question, why didn't they just enclose Webb in a giant tube? I mean, after all, that would have been the best protection for its mirrors. Well, you got to remember that Webb is an infrared telescope, and that means it has to be kept as cold as possible. The tiny amount of heat making it through the sunshield layers warms the mirrors ever so slightly, and that heat needs to be radiated away. An enclosure would trap that heat and warm up the mirrors over time. And then there's the extra complexity of just having to figure out how to fold all of that stuff up and deploy it along with everything else, which of course means higher risks and higher costs. In the end, it was more cost-effective to just over-engineer Webb such that it would degrade gracefully over time. Now, if it's any consolation, we know from lived experience just how hard it is to shoot up a telescope. In 1970, a deranged employee at the McDonald Observatory in Texas fired a handgun point blank into the primary mirror of the Harlan J. Smith telescope. However, the bullet holes didn't affect the image quality so much as it just reduced the amount of light it collects. So instead of a 107-inch mirror, the telescope performs as well as a 106-inch mirror. Those holes are still in the telescope's mirror to this day. And yes, it's still being used for science. Meanwhile, Webb is continuing to perform well above the levels it needs to, and despite this impact being a little bit larger than expected, it hasn't affected Webb's operation schedule at all. The instruments are still being commissioned, and the Where is Webb website is showing the current status of all 17 instrument modes as they are each being readied for science. And if that weren't cool enough, NASA announced that the first full-color images and spectra will be publicly released on Tuesday, July 12th. Now, we've already seen some images, but remember, these are monochromatic test images that were used to verify the alignment of Webb's mirrors. But soon, we're going to witness the power of this fully operational space telescope. And no, I have no idea what the images are going to be of, but that's okay, because we're going to go live on that day on this channel and geek out on those first images together. And that's partly because of these fantastic people right here, my patrons, who are helping to keep Launchpad Astronomy going. And I'd like to welcome Abe Allianz, Daniel, Jacob Harris, Floris Messek, Hans Christian Sievertson, and Adam Wagner as my newest supporters. Thank you so much, and if you'd like to join me on this journey through this incredible universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay curious, my friend.